All right, let's take a look at Unit 2. Unit 2 was more on putting together reasons for why we do what we do, and then coming up with a whole set of proofs. And in this section, we only did algebraic proofs, which means with equations. We didn't do any geometric proofs really yet. That came on later. So we started out with looking at how can we draw conclusions based on patterns. We can find a pattern here, then we can figure out what comes next. We also looked at disproving a statement using counterexamples, which we'll see down there, and then identifying parts of a conditional statement with a hypothesis and conclusion, and then writing the converse, inverse, and contrapositive of a conditional statement. So all of those are coming up with examples below. So when we first see a pattern like this, from -15 to -6 to 3, we say, okay, how did you get from one to the next? In this case, -15 plus 9 gets me -6, plus 9 gets me 3. So my pattern is that it's each term plus 9 to get the next term. So then my next two terms in my sequence, well, 3 plus 9 is 12, and 12 plus 9 is 21. In this case, I'm going from 5 to 11, and then 11 to 13, 13 to 19, 19 to 21. So let's see, I think 5 to 11, that's going to be a plus 6. But then 11 to 13 is only plus 2. 13 to 19, let's see, well, that's plus 6 again. 19 to 21 plus 2. So I've got actually a pattern inside my pattern. I've got first plus 6, then plus 2, then plus 6, then plus 2. So this is plus 6. Plus 2, so then 29 plus 6 is going to be 35, and 35 plus 2 is 37. So my patterns aren't always addition or subtraction. They could also be multiplication. They can also be with repeated shapes or repeated patterns, repeated colors, that kind of thing. Then we looked at how can I disprove a certain statement using a counterexample. So here's a statement that says two complementary angles, remember complementary means they add to 90 degrees, are not congruent. So you might first say, oh yeah, well, I mean, I can have 30 plus 60, that gives me 90. But if I can come up with one example that is opposite of this, so if I can think of two complementary angles that are congruent, then this statement is not true. Even if it's true in most cases, even one counterexample will disprove it. So in this case, I'm going to say, well, wait a second, 45 degrees plus 45 degrees, that's 90, and 45 is equal to 45, so there's my counterexample is 45, and 45 are two complementary angles that are congruent. Number 4 says all rhombuses are squares. So if I can find at least one rhombus that is not a square, then I'm good. So I can just draw you a picture. Here's a rhombus. Again, remember rhombus is all sides are congruent, so that all 4 sides are congruent, but it's definitely not a square. And number 5, if a three-dimensional solid has a circular base, then it is a cylinder. So again, you're thinking, okay, well, cylinder, great, whoops, I'm not very good at drawing, and that actually gave me a hint of where I should go next. I could actually have a three-dimensional solid with a circular base that is a cone. So there's a counterexample that will disprove this statement. From there, we wanted to be able to turn these statements around to write converse, inverse, and contrapositive of each statement, and then decide if they're true or false. So again, the first part of a statement after the if, this is called the hypothesis, and the part that comes after the then is called the conclusion. Sometimes they're not written with an if and then, we have to rewrite them as if and then in order to be able to figure the rest of these out. So inverse statements pretty much just switch the hypothesis and conclusion. So if my original statement says, if a quadrilateral is a rectangle, then it is a parallelogram, switch hypothesis and conclusion. Again, I talked about, nope, I did this in the wrong order. Converse, inverse, contrapositive, but I switched it here. Sorry, converse. Converse shoes, think switching your shoes on the wrong foot. I'm going to switch the hypothesis and conclusion. So if a quadrilateral is a parallelogram, I'm going to abbreviate some things just so I don't have to write everything. If a quadrilateral is a parallelogram, then it is a rectangle. So again, converse, think switch your feet, switch hypothesis and conclusion, versus inverse. Inverse is a not. We make each of these into a negative statement. So if a quadrilateral is not a rectangle, then it is not a parallelogram. We don't switch anything. So if a quad is not a rectangle, then not a parallelogram. Make them both negative. And the contrapositive does both of these things. So it's going to switch the hypothesis and conclusion from the original and make them both a not statement. So if a quad is not a parallelogram, then it is not a rectangle. And then for each of these, we want to think about the truth value. If a quadrilateral is a rectangle, then it is a parallelogram, but we know that, yes, rectangles are parallelograms, so this is true. This is inverse says if a quadrilateral is not a rectangle, then it is not a parallelogram. Well, I can think of a parallelogram that is not a rectangle, that is still a parallelogram. So this is a parallelogram, so that is a quadrilateral that is not a rectangle, but it is still a parallelogram, so this is going to be a false statement. If a quadrilateral is a parallelogram, then it is a rectangle. So this is saying if I have any parallelogram, it has to be a rectangle, also false. If a quadrilateral is not a parallelogram, then it is not a rectangle. This is true because all rectangles have to be parallelograms. If I have a quadrilateral that's not a parallelogram, there's no way it can be a rectangle. All right, then we had two sections that were on intro to proofs and writing proofs where we talked about the different identities that we could have, the addition property of equality, multiplication property of equality, symmetric property, reflexive property. So if you don't remember these, you might have to go back and take a look at sections 2.2 and 2.3. In section 2.2, we were basically just doing it kind of one step at a time or filling in the blank of a proof that was already mostly written for us, and then 2.3, we had to write the proof ourselves with all our reasoning. So if we take a look at a few examples, the first one says, given that 2x equals 10, we can conclude that x equals 5, and we get there by dividing both sides by 2. So this would be the division property. You could call it the division property of equality, but division property, that's enough for me. Given a measure of, sorry, there's a bit of a mistake with that one. So given measure of angle A, we can conclude that an angle is equal to itself. This is called the reflexive property. Reflexive. We use this a lot with triangle congruence when two triangles shared a side and we wanted to say, well, that side is automatically congruent. And then the last one, if I have x plus 25 is equal to 90, I can conclude that x equals 65. Again, this is when you subtracted 25 from both sides. So this is the subtraction property of equality. So again, you might want to look back at section 2.2 just to refresh yourself on what the different properties are. And then in section 2.3, we kind of expanded that so that we had to write all our own proofs and give the reasons for each of them. So we always started off, our first line was always the given, so 100 plus 4 times x minus 1 equals 132. And our reason was that that was given to us. And then from there we would go solving this equation and figuring out our reasons as we go along. So I might do for mine, subtract 100 from each side. So I'll go 4 equals x minus 1. Sorry, 4 times x minus 1 equals 32. And that would be the subtraction property. Then after that, you could either divide both sides by 4 or distribute it in. So if we did the distributive property, it would be 4x minus 4 equals 32. That would be my distributive property. And then from there, I might add 4 to both sides. So I get 4x equals 36. And I would call that the addition property. And then I would divide both sides by 4 to get x by itself, so I'd get x equals 9, and that would be, again, the division property. And depending on what order you did your steps in, you might decide to distribute first. You could collect like terms, and yours might look a little bit different. But the idea is that each step that you do to get down to x equals 9, that's what we're trying to end with, should be justified by some property. All right, that's it for Unit 2. Good luck with your own practicing.